The heavy, still weight of a summer afternoon pushes temperatures past the point of human patience. Historically, escaping the tension of that sweltering concrete meant climbing up to a rooftop just to find a faint breeze. Today, we just flip a switch. Within seconds, a machine delivers an instant rush of relief. For decades, manufacturers proudly marketed these boxes as modern miracles, appliances that simply manufactured winter on demand. But cold is not something we can actually generate. In physics, cold does not exist as a standalone property. It is strictly defined as the absence of thermal energy. If the unit on your wall cannot pull cold out of thin air, it has to do something much more aggressive. It operates as a high-speed thermal extraction device. Creating true comfort inside a room requires systematically capturing the existing heat and forcefully evicting it into the outside void. This diagram maps the unbroken pipeline bridging the inside of your home to the outside world, filled with refrigerant. Zooming in, the evaporator coil holds deeply cold, low-pressure liquid. As warm air washes over the metal coil, the cold liquid rapidly absorbs that thermal energy and instantly boils, evaporating into an active gas. The air passing through the unit has now been robbed of its heat. When a fan blows that depleted air back into your living room, your skin physically interprets the lack of thermal energy as a cold draft. Back inside the system, the warm refrigerant gas carries the stolen heat out of the room, entering the powerful mechanical heart of the operation, the compressor. Heat naturally flows from hot to cold. To force the room's heat out into a blazing yard, the machine must artificially spike the fluid's temperature. The compressor violently squeezes the gas, packing the molecules so tightly together that the temperature flares far higher than the outside air. Now carrying a highly concentrated thermal payload, the superheated gas travels to the outdoor unit, which acts as the designated atmospheric dumping ground. Look at this section of the system, the condenser coil. Because the compressed gas inside is significantly hotter than the summer air, thermodynamics take over. The heat naturally radiates out of the metal tubing and flows into the environment. As the high-pressure gas sheds its thermal energy, it cools down and condenses back into a dense, heavy liquid state. This physical transfer is exactly why the large fan sitting in your yard feels hot to the touch and blasts warm air onto your grass. It is actively throwing your living room's heat into the outdoor atmosphere. The fluid is almost ready to return indoors, but it is highly pressurized. Forcing the liquid through the expansion valve hits a tiny bottleneck. The sudden expansion causes a massive pressure drop, and its temperature plummets instantly. The fluid is now perfectly reset, freezing cold, low in pressure, and prepared to cross the threshold back into the house to steal more heat. This four-step journey is relentless. It loops endlessly, second by second, pulling heat inside and expelling it outside, until the thermostat dictates the room is satisfactory. Scale this up to a skyline, and you see millions of these systems operating simultaneously. Colossal industrial units violently pull heat out of high-rises and endlessly dump it into the urban atmosphere. Fighting the natural flow of thermodynamics comes at a steep price. Running the mechanical compressor to force heat outward requires immense, continuous amounts of electrical power from the grid. To measure the efficiency of this process, engineers rely on a specific formula. This graphic illustrates a metric called the coefficient of performance, or COP, which weighs the amount of heat successfully removed against the electrical input required to run the compressor. Maximizing that COP is the constant objective, extracting a greater degree of thermal energy, while siphoning the absolute minimum amount of electricity. The next time a cold draft brushes against your skin on a summer afternoon, you know exactly what is happening inside the machinery on your wall. Every degree of relief is the product of precise thermodynamic control, a silent machine looping indefinitely to force energy out of the room and hold the summer at bay.
Help us reach the target of 150 subscribers. Don't forget to like and share this video.